Hi guys, and welcome to today's video on, believe it or not, set notation and sets of numbers. Now, I don't know about you, but have you seriously got nothing better to do? This video has all the appeal of watching paint dry, but I'm going to do my level best to make it as interesting as I possibly can. I'm the Maths Guru, and welcome to my channel. And if you already know who I am, then you can skip the next 30 seconds. But if not, can you do me a favour? You see that red doohickey over there that says something along the lines of help me out or show some love or support me? If you can click that, it would be greatly appreciated. Then you become a member of my YouTube family of about 12 people. I'm trying to make it to 20 by the end of this week. So can you help? Hopefully you can. I don't get any money from this. I'm doing this actually for fun. If you could see, I'm currently sitting in my living room with, well, just a random setup. But anyway, too much information. That's about the most interesting part of this video, to be perfectly honest with you. What am I dealing with? Well, this is part of what we call a Headstart course here in Australia, and it ties very much in with the first 4 or so chapters of a textbook, the Cambridge Essential Textbook Series, which if you have it, it is fabulous. And if you don't, then I'm really sorry you're missing out. It is absolutely awesome. But what I hope to achieve by the end of the lesson is to talk about what set notation is, what sets of numbers are, and more importantly, interval notation. Again, I'm already falling asleep thinking about this, all right? There's not a lot of practical stuff, but the one thing I'm going to say now is if you are doing methods 3 and 4 here in Australia or any further study, everything we're about to cover has something to do with graphs. And interval notation is so important. If you can understand what it's talking about, I think probably half the battle is done. That's absolute rubbish. If it was half the battle, then this course would be way easier. But what we have here is a recap. Now, way back in year 10, or for me last week, because I taught this last week, we looked at something called Venn diagrams. You may also have looked at them in probability in methods 1 and 2. And a simple diagram, it was a simple diagrammatic representation of two events happening. Now, as you can see here, I've got an example of a Venn diagram. So what I'm going to do is put epsilon up there, which is my whole sample space. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now what I've put in there are the numbers 1 to 10. That is now my sample space. And if I scroll up a little bit, then what I say here is my sample space. And you'll notice they're written in those curly brackets. Well, I've just introduced you to a set of numbers. This was probably event A, and this was event B. And there was an overlap. Now, not all events will overlap, and in which case they're called mutually exclusive, and we'll get very excited about probability, but we want to get too excited. Venn diagrams are really much the basis of this section, and if you know what you're talking about with the curly brackets and stuff, then again, you're pretty much already there. But the language is important. So as I scroll up and I put here though, 1, 2, 3, 4, 5, these curly brackets are incredibly important. Don't put square brackets, means something completely different. Don't put curved brackets, means something completely different. It has to be those curly brackets there, and they're a nightmare to try and draw. As I've said a moment ago, all of those numbers together, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, are called a set. And an individual element of that set is exactly what I've just called it, an element. An individual number is called an element, or strangely, a member. Now, being bizarre, a member just has no good connotation at all, so I'm going to move off of that completely. But as I normally suggest, Barry, who is that guy who sits in Australia who tries to come up with 100 different ways of talking about the same thing, has been on overdrive here. Why we call it an element or a member, I have no idea, but you need to remember all of the different languages. Now, being part of the in crowd, I try and be humorous here if this is the first video you've watched, because otherwise it's deathly dull. Now, I wish I was part of the in crowd, but I have no friends. No sympathy, please. I chose my life as a maths teacher, and sadly we go to, I don't know, nightclubs or bars, and people say, what do you do for a living? And I go, I'm a maths teacher. And they all leave. It's so bizarre. But anyway, being part of the in crowd. Now, we need to know maths notation. And up until now, I fought everything I can to not do this maths notation, but it's now coming back. And as you can see here, X, and then this little E, and then A. Now, what that means is X is contained within, or in, or is a member of, or belongs to this A, this set of A numbers. Ooh, that's quite exciting, and we're going to use that quite a lot later on, particularly when we get to function notation. But seeing that E in the middle there, as I say here, can stand for as a member of, belongs to, is in. Now, obviously, if they're not in, they're at. So again, as I say here, X, there is within, I'm putting a line through it, means is not included within. And again, an example we have of that in a moment is when we talk about something called the domain. Now, again, that shouldn't be particularly new if you've done methods 1 and 2. But what it says there is that x is contained within the values of 0 to 10. Now, because I have no context of the question, I don't know whether those are integers, whether they're real numbers between 0 and 10. I don't know. But that notation is what you're going to have to start using for pretty much everything you do in this course. Now, being part of a clique is awesome because obviously I am a teacher, a maths teacher, and then when I go into the staff room, I'm part of a bigger collective. I'm still a maths teacher, I'm still special, but when I'm in the staff room, I'm part of a bigger collection. So I am actually a subset of teachers. A maths teacher is a subset of teachers. Another example that we can use is, as I'm showing here, we have event A or set A has numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And set B has numbers 3, 6, and 9. Now, obviously, B is fully contained in A. Those numbers are repeated. So what we can say, as I've said here, is that B is, notice you get the C and the line underneath it. That C, and because it looks like a C, and I've done it the wrong way around for you guys doing the camera, that C stands for contained, or it belongs to, or is within, or is subset. So again, more language. Barry, what are you doing? But we need to learn that language. Then I'm feeling hollow and empty. Why would I feel hollow and empty other than the fact that I've just admit to having no friends and being a maths teacher? My life is over. Well, there are times, ladies and gentlemen, where we end up with something called the empty set. What on earth is an empty set? Well, it is literally squiggly bracket and squiggly bracket with absolutely nothing in it. How would that happen? Who knows? But it is possible. And so what you need to know is that that can also be expressed as a 0 with a line through it. Now, if you're a computer programmer, you already know that that means 0. But in this particular instance, when you have an empty set, it is that 0 with a line through it. See how we're zipping through this? Have I done anything mathsy exciting? No, not at all. But it is all important information. Back to our Venn diagram. Now, as I said to my year 10s a couple of weeks ago, Venn diagrams are really, really easy because what you're actually doing is you're trying to find various probabilities or numbers of, and the way we do that is we look at sections of our Venn diagram. So if I get epsilon there again, that doesn't look like an epsilon, that looks like a C, so let's try that again. And I do 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's put 10 out there. I know it's different from before, don't worry about it. Here is event A. And here is event B. Now, what we can do is we can do things like find the number of elements in set A. How? In this situation, using my Venn diagram to count them. So 1, 2, 3, 4, 5, 6. There are 7 elements in set A. Don't forget this section here is my overlap. Yes, do you remember the word? Intersection. Fabulous. If I wanted to look at NB, what would I have? Well, that's the number of elements in B. And that in that situation would be 4, because the 6 and 7 are still in B, they're in A, and they're in B. What about the probability of A and B? So finding the probability of A and B, well, and is that intersection. How many numbers do we have? We have 2 numbers. Out of how many in total? 10. And so we have 5. And we could go on. But the important parts of this graph are, generally speaking, something like N of A union B and N intersection B. So that union and that intersection are really, really important to us. Now, union, if you remember, would be when we take all of this and add them together. All right, so all of that. So in this situation, if I wanted N of A union B, then I'd go 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 numbers in total contained within A and B, and I don't count the overlap twice. So very, very important. And I did say that we're throwing conditional probabilities, but we also need to now understand that we can have differences of sets. So we're looking at, well, what's different between 2 sets of numbers? And this slash notation becomes very, very important later on, again in function notation. Don't worry about it if you don't understand what I mean by function notation. Hopefully you do, but really, really important. So as I say here, I've got 2 examples. I've got A and B. Now, A with a slash B means which objects in A are not in B. Okay, so which objects in A are not in B? And hopefully, as you can see here, if I look at the objects that are A but not in B, that just leaves 1 and 3. Again, curly brackets, 1, 3. Now that's very different from if I write square brackets. Now in that situation, we get to what we call interval notation, and I'll come to that in just a second, but that means all the numbers between 1 and 3, including 1 and 3. So we need to be very, very careful with the brackets that we use to describe sets and intervals. Right, now, numbers can be classified into 4 main categories. 5 if you include the fact that every single number in the world is what we call a real number. And did you notice what I did there? The double line and the R. That's part of what we call real numbers. Every number from minus infinity to infinity is a real number. Then we cut things down into what we call the natural numbers. So the natural numbers are basically numbers 0, 1, 2, oops, try that one again. Are the numbers 0, 1, 2, 3, 4, 5. Now notice they are the whole numbers starting at 0 and going positive. Then we have integers. Now integers is any whole number at all that can be both positive and negative. So examples are minus 3, minus 2, minus 1, 0, 1, 2, 3. And I've seen the word integer used in exams all the time. And it's surprising the number of people who get thrown by that one word. They go, what's an integer? Try and learn it. It's just a whole number that can be positive and negative. A rational number is a number that can be expressed as a fraction. Right, so most numbers can be expressed as a fraction. 27 on 2 is a rational number. Well, I don't know, there's all sorts. A half is a rational number. And then we get irrational numbers. And irrational numbers are numbers that just ain't rational. Lol. So an irrational number would be a square root of 2, for example, or pi, or e. Any of those numbers which can't be written as a fraction. All right. They are what we call irrational numbers. Now, pi has still yet to be finished, right? It goes on and on and on to infinity and beyond. So it's highly unlikely that pi will ever be able to be expressed as a fraction. Now, you might turn around and say, well, hold on, isn't pi 22 over 7? That's what I've been taught. No, 22 on 7 is an approximation, right? So it'll give you close to an approximation for pi, and I really don't know how many decimal places, but yes, it's close, but it's actually not pi. Root 2, again, can't be written as a fraction. And you're going to say, what about root 2 on 1? Yeah, that's a fraction, but unfortunately you can't have a square root sign. So this thing sort of goes on. Now, for each of these subsets, there is an individual letter that stands for, and the one I think you're going to see the most of is that letter R, that double R. It stands for real numbers, and that is all numbers. It includes decimals, fractions, whole numbers, integers, natural numbers, the whole works. So get used to the idea of that R. Now we can describe sets of numbers in lots of different ways, and we're working very much to almost the end of this video with interval notation, probably the most important part of the video, and you probably wonder why I don't do that first. Keep you watching. So when we describe a set, we can do it in lots of different ways, and here I show you 4 different ways. So the first thing is you'll notice those curly brackets, which stands for a set of numbers. And the first one says x with a colon, 0, x, and 1. Now in that situation, what it's saying is our numbers, our x values, or our numbers in this set are going to be created by using that part of my identity, that notation that it says x can basically fall between all values between 0 and 1. But that don't include 0 and 1. Now, how do we know they don't include? Because otherwise I would have a less than or greater than or equal to sign. Because we don't have that, it would be all values between 0 and 1, but not including. What about this value here? Well, this set of numbers would be 3 and more. Well, actually, I can't even give you examples because this would be real numbers. But what it is suggesting there is, again, x, or the values inside my set, would be decided by x is greater than or equal to 3. So values of 3 and above to infinity. This stuff is awesome. Here, we've now thrown in some sort of limitation on the numbers. So it says I want the values of x, where x has got to be greater than 0, but that x is in. See, we've started using that notation now. In, what does the value of q stand for? Well, that q stands for rational numbers. So we're only allowed numbers there that can be expressed as a fraction. Ooh, this stuff is awesome. So what did that say? So q, how do you do a double q? That's interesting. Never had to do that before. And then in this situation here, ramping it up, 2n. Where n is equal to 0, 1, 2, and so it goes on. So my set for that would start with 0, 2, 4, 6, 8, and so it goes on. So that's just another way of describing all my even numbers, yeah? Now, obviously, all my positive even numbers, including the value of 0. So that's one way of describing a set, and you have to get used to it. But the one we use the most is interval notation, and this is this one here. So, ladies and gentlemen, that thing there is interval notation. And we use it to describe domains and ranges. Again, don't rush with it, that's coming in the next video. But what is a domain and a range? Well, it is a collection of numbers that describe a horizontal movement and a vertical movement. So if we look at this interval notation here, what on earth does 0 to infinity mean? Now, obviously you can see one of them has a square bracket and one of them has a curved bracket. Well, the good news is a square bracket includes the number. So in this situation here, we're going to have all the numbers from 0 all the way up to infinity, and we're going to include that value of 0. But why does infinity have a curved bracket? What does a curved bracket mean? A curved bracket basically means it cannot include it or does not include that value. You're going to say, well, why doesn't it include infinity? Well, believe it or not, infinity isn't really a number. It's a construct. It's a concept. It's an idea. You can't actually write down the physical number of infinity. In fact, if you think about it, we have random expressions like infinity plus 1. And lots of people go, I love you too, no, I love you more, I love you to the world and back, I love you to infinity, I love you to infinity plus 1. Random. Infinity plus 1. Don't even go there. So my advice to you, and this is a big trick, is that infinity always has a curved bracket because it's more a concept than it is an actual number, right? And so if we have a look at this example here, that x and in is talking about a domain, and we're coming to that. I promise you we're coming to that. But in this situation, notice the square brackets. So what that tells me is in that situation is that I'm going to go from -3 to 5 with all numbers in between them. So all real numbers in between them. And I'm going to include -3 and 5. Now I could actually draw that particular instance on a number line. So I could go -3, -2, -1, 0, 1, 2, 3, 4, and 5. Let's make my number line a little bit. So we're including -3, so we'll do a circle with a dot. We're including 5, we'll do a circle and a dot. And then I would join a horizontal line between those two. And that's a number line representation. What about this f of x in big R? Well, f of x is basically a shortcut for my y value. So what this says is it's talking about a range of possible y values. But we're going to come back to that. As I said in another lesson. I keep saying that a lot, I know, but it all interrelates. So let's come up with another example. 0 to 6 with a curved bracket. What would that mean on a number line? Well, it would mean 0, 1, 2, 3, 4, 5, and 6. The curved bracket does not include the 6, so that would be an open circle. The square bracket includes the 0. And so that was a really shonky straight line, but that would describe that interval. Now, again, remember the difference between a curly bracket and those square brackets. Critically important when you do these things. Another one, -infinity to infinity. Yes, to infinity and beyond. That is possible. Notice I have curved brackets on both of those. Why? Well, if infinity is a concept, then -infinity is also a concept as well. In fact, it's a weird concept because you could argue that -infinity bends all the way around and touches infinity, but at that point my mind explodes. There is some shorthand notation for some of the most used intervals because in maths we try and make things easy for ourselves. So the first one we see here is this one here, which is a double R with a floaty plus. Now what that means is all positive real numbers. Now, point of information here, 0 is neither positive or negative. So when you are using this value here, you are doing all values, but not 0. In the same way, we can have R with a minus sign. So that's all negative values, not including 0. So all the way from -infinity all the way up to 0. This one here, R. Now, there should be a slash there, but for some reason my computer has deleted the slash. Now notice that slash, yes, is excluding 0. So we're looking at taking that 0 out. So this would be all real numbers from -infinity to infinity, but not including 0. And you're going to probably say, well, why would that be important? believe it or not, there are some graphs that you can draw that 0 does not exist for. And if you want to know which one, think of the graph of 1 over x or graph of 1 over x squared. If you were to actually plot that using Desmos or your CAS calculator, you'll find out that that does exist for all values of x except 0. So all real value except 0. The last one here is this one. And it's the one that lots of people get wrong. Now imagine I want all the positive real numbers and 0. Now, the way I've said that actually throws people, because a lot of people go, oh, real numbers and 0. Now, that doesn't make any sense. You cannot have a real number and 0. Yes, it has to be all the positive real numbers or 0. And the reason being is 0 cannot coexist at the same time as all those other numbers. It's a bit creepy and weird and confusing, but just remember it's R plus with a U and a 0. So we're almost done, ladies and gentlemen. 2 more examples of number lines. Express 2 to 5 on a number line 2, 3, 4, and 5. Let's put 6 on there just to make it look better. 2 is included because of the square bracket, so a circle with a coloured in. 5 is included, circle with a colour in. And lo and behold, that's expressed on a number line. An interval notation here of -4 to 3. All right, let's draw it that. So -4, -3, -2, -1, 0, 1, 2, and 3. So -4 is not included, 3 is included, and join the 2 together. What about one more if we had, I don't know, 4 to infinity? Now notice the curved brackets. Here we go. So 4, 5, 6, 7, 8, 9. Now obviously I'm not going to keep going to infinity, I've just given enough numbers. I'm going to do a circle and then an arrow pointing to infinity and beyond. Now ladies and gentlemen, I promise if you have stuck with me this far, you are just legends, actually. I promise you there's more maths and more excitement coming soon. The next few videos, I'm afraid, are all terminology that's important that you understand. The number of people who actually start this course and go, oh, I don't understand what a domain is. I don't understand what a range is. I've never understood what it means by a set. Well, now is the time you need to learn it. I promise you, it's so, so important. All right, ready for a 45-second Twitter recap? I should go. Hi and welcome, and today we have dealt with set notation and sets of numbers. Now this is quite a lot of stuff, to be perfectly honest with you, that we went through. We started off by looking at Venn diagrams, and we ideated the idea of sample spaces with elements and members, and knew that the whole thing was called a set. We wanted to be part of the in crowd, and we knew that that little E sign had something to do with being a part of, a member of, or belongs to, or is in. See what I did there? I'm part of a clique. I'm a maths teacher. Don't tell everyone out there because I've already got no social life. And we looked at what it meant to be contained within a subset and how to feel hollow and empty with that empty set. Why we would have an empty set, I've got no ideas. We went back to Venn diagrams before looking at celebrating our differences about the fact is that sometimes we want to exclude people. And then we looked at the number systems, natural, integers, regional, and irrational before describing sets. And lastly, looking at interval notations, which was the most important part of this lesson. And breathe. All right, ladies and gentlemen, that is it. I am done for this lesson. Thank you very much for kicking in and watching. I promise you in about 4 or 5 videos time, it gets a lot more exciting and some real maths. If you haven't already, can you do me the honour of please subscribing by clicking that doohickey there? You have? You haven't? Oh, you are hard to please. Otherwise, there is a video loading for you over there of a very similar nature. All right, take care. Maths Guru out.